Good morning, everyone. My name is Rahul Das, and currently I'm doing my master's in Construction and Infrastructure Management at Department of Civil and Environmental Engineering at University of Nevada, Las Vegas. Today I'm going to talk about a study which I did into a cracks, which I saw into a creek bridge that was built with the self-propelled modular transporters or the SPMTs. So the et al. 2020 Kim et al. 2020 study looks into the whether these cracks were caused by the SPMTs or the building method or by the way the structure behaved. So to understand well about the study, we need to understand what is the skewed breeze are. So skewed breeze are often used in the rough landscapes and the cities, but they pose special problems because their shape isn't straight. So this study is very important because of the figuring out why cracks happens and how this can help builders make breezes in the future and avoid problem like this. So moving on to the introduction slide. This study is mostly about a curved skewed bridge that got a full deck crack soon after it was built. So these cracks were especially scary because they meant or they could have a lot of problems with the long-term stability. So the main goal of the study was to find out like these cracks were caused by the SPMT ways or of the buildings or if they were bound to happen because of the breezes and the shape border conditions. Moving on to like why is this study so much important? So skewed bridges are needed to connect equipment that is in a limited area, but they don't behave like a straight bridges in the same way. So cracks in a bridge can cause a long-term damage that costs a lot to fix and shorten its life. You can see this point in the image. The top picture shows the site of the bridge, and the that bottom picture shows that how expansion joints and the corners that aren't straight. These cracks were photographed and used as a straight point for the study. So moving on to the one of the important part of our study, which is methodology. So the study employed a combinations of inspections, computational analysis, and also the material testing to determine the cause of cracking in the skewed breezes. So the engineers conducted the site inspection where they visually documented the crack patterns, measured their extents, and also categorized them based on their locations and their severities. So this observation provided initial insights into the areas which were most affected by the stress concentration. To furthermore understand and structural behavior, the researchers performed the FEA, which is also called the finite element analysis, using the Diana software. This non-linear simulations allowed them to assess how the bridge deck respond to different conditions, particularly focusing on the influence of the deck skewness, also the boundary conditions and the bearing configurations. Moreover, by simulating these variables, the researchers could identify whether the observed cracking resulted from inherent designs or the issues or the external factors such as the temperature fluctuations and also the load distribution. In addition to the structural analysis, the material testing was also conducted to rule out any potential weakness in the concrete itself. You see in the point 4 petrographic analysis. So petrographic analysis of core samples help determine whether materials properties contributed to the cracking. So this step completely ensured that the issues were not caused by the defects in the concrete mixtures, but rather by the structural and also the thermal stresses. Moving on to the pictures, you see the upper pictures in the slide that completely illustrates the bridge's structural system, highlighting the spans, supports locations, and also the bearing configuration that influence the stress distribution. Whereas the lower picture, the below picture, illustrates the reinforcement plan, which plays a crucial role in determining how stress are absorbed and how they are distributed throughout the bridge deck. Now let us jump to the key findings. So the study found that the differential thermal expansions and also the contractions were the factors that were causing the stress buildups and also the skewed bridge deck. So unlike the conventional straight bridges, skewed decks experience uneven stress distributions, which leads to the higher concentration in the specific areas. A major contributor to the cracking was the semi-integral abutment designs, which restricted the deck's natural movements. So this caused the stress movement to accumulate at the sharp corners, making this area highly susceptible to the cracking. Additionally, bearing conditions played a role as they failed to adequately accommodate the deck's thermal and structural movements, further intensifying their stress levels. So, crucially, the study concluded that the SPMTs, which is self-propelled modular transporters, method was not only the root cause of the cracks. Similarly, the structural issues would have also occurred with the conventional and also the construction method, suggesting that the problem was more related to the design constraint rather than the constructional approach. You can look into the picture here. This Diana software models helped the researchers analyze the stress distributions and also the predicting high stress zones and validating their findings. So, moving on to the conclusions and also to the recommendations. So, this study highlights that the skewed breezes experience the higher stress concentrations and also at the sharp corners due to the uneven thermal expansions and also due to the load distributions. So this expansions and load distribution create the stress buildup if and which is not addressed can lead to the premature cracking and long-term durability issues. So to mitigate these modifications and in the bearing and in the expansion, joints are essential. So instead of rigid supports, using flexible expansion joints can help accommodate the movements and also reduce the internal stressness. Another key finding is the impact of semi-integral abutments. So while they reduce the maintenance, they restrict the deck movement, increasing the stress and also the crack formation. So a better approach would be a hybrid system that allowed the control movements like expansions, cushions or also the side bearings. Similarly, reinforcement techniques plays a crucial role in the stress distribution. Using the fan-shaped reinforcement patterns can help absorb and redistribute the forces more effectively, reducing the likelihood of the cracks and also the acute angles. You can see the point at the image. The diagram here visually represents the effects on the stress on the skewed breezes, and it also shows how stress accumulates in the specific areas, highlighting the importance of the improved joints and also the bearing conditions. Further research is needed on the alternative bearing systems and also to the construction methods to accumulate skew-induced stresses. And also the real-time monitoring with the strain gauges and thermal sensors can validate the numerical models and improve the future breezes design. So implementing these recommendations can lead to more durable and safer breezes with the reduce and maintenance of the needs. So moving on to the critic. So this articles provide a valuable insights into the cause of cracking into the skewed breezes, particularly through the use of FEA, that is the finite element analysis, combined with the real world data. So one of its greatest strength is how it integrates computational modeling with the field inspections, making the findings more reliable. So by using the advanced simulations, the researchers were able to pinpoint how stress develops in different parts of the bridge and identify key factors influencing the crack formations. So this combinations analysis method ensures a more accurate representation of a real world conditions rather than relying on solely on the theoretical assumptions. Another strong aspect of the study is the clear recognition of the factors which are responsible for the cracking, such as thermal expansions, skewed geometries, and also the semi-integral abutments. So, by isolating these variables, the study provides actionable recommendations for improving future breezes design. However, there are certain limitations. So, one key issue is assumption of regular materials properties throughout the breeze structure. So, in real world conditions, material can have inconsistencies due to variations in the quality, temperature, or the curing process. So, these small differences can significantly impact the stress distribution, meaning the model might not capture all the real life behaviors accurately. So, additionally, while the study provides a strong evaluation of the current design, it also does not explore the alternative construction methods in the depth. Like for example, could different bearing configurations or pre-stressing techniques reduce this cracking even further? What do you say? So, the research is needed to test alternative solutions and validate them under the real world conditions. Also, you can see the image, the diagram on the slides different that illustrates the different skew angles and also their effects on the stress contributions. It illustrates how stress accumulates at the acure corners due to skewness, highlighting why improved reinforcements and the bearing designs are necessary. So, in conclusion, while this study makes important contribution to understanding the skewed breach behavior, expanding the research into the alternative construction techniques and the real-world material variations would further strengthen its findings. So these are one of the important critics which I have found from the study. So moving on to the errors and the improvements. So while the study provides the crucial insights into the cracking issues in the screwed breezes, these are the areas where improvements can be made. So one of the key recommendation is the use of the outdoor instrumentation such as the pressure gauge, temperature monitors to validate the findings in the real conditions. This would help in capturing the actual thermal effects and also the stress distribution over time rather than rather than relying solely on the computational models. Another improvement involves using parametric analysis to test various joint designs, stranding methods, and bearing system. So, by exploring a range of configurations, researchers can identify the most effective solution to minimize the stress concentration in the skewed breezes. Additionally, more research is needed to compare the SPMTs based construction with the traditional building methods to determine if one approach significantly reduces the cracking risk over the long term. You see the image, the diagram on the slide illustrate how temperature distribution across the bridge deck influence the thermal stress and contributes to the cracking. So the highlights need for the better expansion joints design and also the reinforcement strategies to mitigate this effect. Lastly, the long-term effect of the creep and the shrinkage on the bridge performance should be further investigated. Over time, these factors can amplify and also the existing stress conditions can lead to more and more significant structural concerns. Addressing this issue through material selections and also the improved construction techniques will be essential in ensuring the durability of future skewed breezes. So the next slide is the references. So this slide presents the primary reference for this study by the 2020 paper by the Chorzepa, also the Durham and also the Solae. The research published in the Journal of the Performance of the Constructed Facilities investigates the cause of the cracks in the skewed breezes construction using the self-propeller modular transporters, that is the SPMTs. The study integrates the field inspections, the computational analysis, and the material testings to identify the key factors to contributing for the structural distress, and also the citations here provided access the full article which offer a detailed explanation of the methodology findings and recommendations. So this research serves a valuable resource of the understandings, bridges, and influence of the construction technique on the long-term performance. So that concludes my presentation and thank you for your time and attention. I hope this analysis has provided an insight into the structural challenges of the skewed breezes and also the role of the construction methods in the influencing durability. If you have any question or would like to discuss any part of the studies further, I would be happy to answer. Once again, I appreciate your engagement and I look forward to any feedbacks or discussions on how these findings can apply to the future breeze designs. Thank you and have a great day.